I am this guy, Peter Harrington, and I'm here to talk about becoming a data-driven organization with machine learning. I just want to say, first of all, thanks for coming out. It's 8:30 right now in Central Time, which is 6:30 California time. So who here came from the West Coast, Pacific? Wow. Okay, a lot of people. I came from there too, so it's 6:30. You could be in bed or you could be having breakfast, but you chose to came here. So I just want to say thank you, and I appreciate that. Okay. The next is the goals for this talk. I'm just going to introduce machine learning. I'm going to talk about how we can take machine learning outside of the organization, outside of the engineering organization that got left off. And I'm going to share some experience from the trenches or some valuable things I've learned from, going from pure application to, from pure just theory to actually applying this in an agile environment, applying this in a growing company. So I think those things are very useful. And lastly, simplicity. So I have the material I have, a third of it I took from another talk I gave at a high school. So it was actually a high school freshman. So it's going to be real. Some of it is really dumbed down. So if you're looking for like really fancy algorithms and stuff, this isn't the place for it. I mean, I'll talk about some machine learning algorithms, but I'm not going to get into the details. I'd rather insult a few people's intelligence and but teach some things to some people who didn't know that, then show something that's really fancy and make a few that only one person in the room understands to make myself look good. So some of this is dumbed down. If I'm going to insult your intelligence or experience, I'm sorry, but that's what I've decided to do. I just want to point out they're really smart high school students. High school has a $100 million endowment, which is more than most of the universities in the U.S. So there are smart high school students, but still, some of it was, a third of the material was from a talk I gave to 9th graders. Okay. And then to accomplish this is the exact agenda. I'm going to introduce myself and the current company I work for to motivate why I should be giving this. Next, I'm going to define data-driven and machine learning. Then we're going to go over just some common tasks in machine learning. Once again, if you're familiar with machine learning, you might be a little bit bored with that. Maybe you'll find something useful. Then I'll go over a sample of some algorithms. I've got some code. And the code, I'm going to apologize, is actually written in Python. I'm sorry about that, but that's what we use for prototyping a lot of our stuff. And we have Java versions. We use Java versions in production, but I just didn't feel that the Java version was slide-worthy. Like, it would probably take up a whole slide of code just to get across what I can get across in 4 or 5 lines in Python. So the examples I brought are Python. And then these yellow starred items are things I've learned from the trenches, and they're interpretable machine learning. How do you handle machine learning in agile development? And then what is this term data scientist we hear so often recently? And what does it really mean? Okay. So I've written a book called Machine Learning in Action, and it's actually written in English, but it's been translated to a couple languages, and these are just snapshots of the Korean and the Chinese versions. And it's about 300 or 400 pages and I based it on like the top. Okay, let me take a step back. I feel so strongly about doing data-driven everything that the contents of this book were data-driven. So there was a survey taken in 2007 at a machine learning conference, and the topics of this book are based on that survey. And the survey was, what do you think are the top 10 most important machine learning algorithms? So most of them are contained in there. There's one called PageRank, which you may have heard of, which is like the Google search is based off of. And I just left that out because that had been written so many other times. It was, I didn't feel like I was bringing anything new. So I didn't write about that. And then this book was one of the best-selling developer books in 2012. It was went to print in May 2012, and it was the third best-selling ebook of 2012 and the 7th best-selling paper book in the developer category. So I think at that time, a lot of developers started looking at data science, machine learning, data mining, and it was a right time. It wasn't that I wrote the awesomest book, but it was the right time to publish something in that space. Okay, I currently work for this company called HG Data, and we have a database of what companies are using what products, and we sell this to sales and marketing people, and they are willing to pay us for this. So let me see something. How many people here have ever met a salesperson inside of their company? Oh, a lot. Oh, okay. Prior to this, my company previous to this, I had never met a salesperson before. Like a salesperson at my own company, maybe at some other company, but a lot of engineers don't understand what salespeople do. So we have data of what companies are using what products and sales. And usually this is things with a high lifetime value, like maybe around $100,000 or more. We're not really tracking what Snickers bars are, who buys Snickers bars or pencils. And sales and marketing people will pay us for this information. And so we collect this from unstructured text. So we have a bunch of different document sources like press release, job postings, resumes, and it's my job to figure out from this unstructured text these triples, like what company is buying from what other company and what product they're buying and the date and the location. And we use a lot of machine learning internally to do this, and then we sell it. We sell the data. So we don't make any software. Whenever we have to deal with lawyers or something, there's an audit. I have to try to remind them. They'll audit our open source software to make sure we're not violating any copyright or anything. And I try to tell them we don't sell any software. Okay, who cares? We sell data, but that happens. And then this year we won this Gartner Cool Vendor Award. Yeah, so we do this using natural language processing, which is like machine learning applied to text. And then we've created like a knowledge graph of business information. We do this over 1.5 billion documents daily, and we try to keep our infrastructure costs down. So we use a lot of Java. And then lastly, I would end this with some spam. We are hiring, and we love Java engineers. We're hiring for 2 locations. One is in Santa Barbara, and there's the other one is in Sunnyvale, where I work is in Sunnyvale, California. And in Santa Barbara, there's 3 universities, and it's got a population of 80,000 people. It's right on the beach. There's a lot of physically fit people. You know, whatever you're interested in, there's definitely attractive people there. Or you can work in Sunnyvale, where we have a bunch of people who think they're Steve Jobs and call themselves iconoclasts. And so it's up to you. Yeah, I choose to live in Sunnyvale, where we have a Target, but that's just my choice. Okay, I'll end the spam here, and we'll get on with this. Okay. So data-driven is a buzzword that comes up, but I think it's really important. And it's become more important recently, or it's become more popularized recently with things like the movie and the book Moneyball by Michael Lewis, where they actually took data and applied it to baseball. Or you look at a lot of businesses, and some businesses will have a CEO that says, you know, we're going to do this, damn it, because I like it. But I think a lot of really successful companies, and only in the future, only successful companies that use data-driven, make data-driven decisions are going to be the only successful ones. I think you're just going to get your lunch eaten by other companies if you stick around. And the problem is a lot of companies that you may think are data-driven, and they publish shirts that say I love data or I heart data. They don't really use it to make decisions. So they may have plenty of feedback from their customers, but they'll release a product based on what they think, what some person in marketing just feels that morning, or maybe what the CEO feels, and it's just the wrong approach. Okay, so the definition that I stole from Wikipedia was data-driven means that progress in an activity is compelled by data rather than intuition or personal experience. So you should be working for a data-driven company. And if you're not, you should do what you can to bring that out. Bring the data that you're seeing on a daily basis out. And one of the things you can do is with machine learning, you can distill down a bunch of noisy data into some really quick bullet points that you could bring to the CEO or someone, your boss, someone that's not looking at data on a daily basis. Or maybe they are looking at data, but they don't know what the hell it means. It might have 1,000 features and 100 million rows, but what does that mean? Okay. So what exactly is machine learning? And this is the first stab it will take at a definition. It's some tools that allow a machine to learn from data. So we have some data and we want the machine to tell us something about it. And we may want it to tell us about that because we're trying to build an application for it, or we are trying to learn what the data means for our own education. So I will show an example that may seem simple to you. We have some data here, and this is children's weight and their height. And so we have this, and we want to generalize this. So what do? We create a best fit line. Like, I'm sure everyone in this room can do this in Excel. It's pretty easy. And you probably could do this in high school. The high schoolers I showed this to knew what it was, and they had no problem with it. So it's pretty easy. What's this telling us? But this is, I think, the simplest example of machine learning, where we've taken some data we had and through some sort of algorithm, regularly squares in this example, the machine has told us something about it. And it says for these children, on the majority fit, their height can be described as 0.922 times their weight plus 12.472. Okay, so that, just keeping that in mind, that is, we've learned something, or the machine's given us something from this. Okay, the other part of the definition I want to add is that these are tools that can make, we can make a decision from non-deterministic data. So if we were to look at this and we were to ask someone to say, describe this data to me, and they might give us that best fit line, but it's wrong on a few examples. There's examples above and below. So our answer isn't exact for everything. Our answer is close, and we can even establish a confidence bound. We can establish like how well this is fitting. But this is, it answers, it makes, we can make non-deterministic decisions based on this. Okay, so in machine learning, there's a couple of common tasks. Usually you'll see supervised learning and unsupervised learning. So in supervised learning, we have regression, which I just showed you the example of. Everyone knows that. You're predicting a numeric value based on some inputs. Another one is classification, where we're predicting the category of something. And this may be simple as 2 categories, like spam or not spam. Or we may have many more features. Maybe it might be as many as 100. You might be predicting one of 100 labels. Those are 2 categories of supervised learning. Then there's unsupervised learning, which says we don't really have a target value. So in supervised learning, we're given a target value and we're given some data, and it says figure out some relationship between these 2. And then in unsupervised learning, you don't have a target value. So it just says, here's some data, tell me what the hell this means. And then some common ways to do that are clustering, where you would say, okay, put the data into X or N different groups. And there's other things like association rule modeling, where a famous example that our business school students hear of is men who buy diapers commonly buy beer. At one grocery store in the Midwest, they observed that it was on Thursday nights, men who were buying diapers frequently bought beer. And they just made a note of this. But they could have taken advantage of that by putting the beer right next to the diapers, or increasing the price of it, a number of things. So that's called association rule mining. And even before association rule mining, you have to generate these frequent item sets, like what do people frequently buy together? And that's a big task. Okay, topic modeling is something else that is another task in unsupervised learning. So you're given a stack of documents, and you want to learn what the hell are these documents talking about? So a common example, and this has been going on for a while actually, is lawyers, to screw with each other, they will give each other a lot of documents, like so many that it's prohibitively expensive. Like even if they hire dirt wage paralegals in remote locations, they can't go through these documents in enough time. So maybe 1 million documents. I was on the plane next to a lawyer who was suing General Motors for some injury, and they had given him close to 1 million documents. He wasn't employing these methods, but I've been at other conferences where there are lawyers doing this. So what they do is they take these 1 million documents and they put it into some algorithm, and it'll spit out top 10 or 15 or whatever topics. And then of these topics, you can drill down and say, okay, what does this topic mean? So if it was, it will be associated either words or sentences that exemplify that topic. And you can probably guess a number of applications where that is important besides the lawyers. And lastly, there's something another common task, or another task, which it doesn't appear in the introductory material that much, is semi-supervised learning, where we have a combination of the supervised and unsupervised. It says, well, can we leverage some unsupervised methods to make better supervised learning decisions? And the case for this might be where you have a lot of unsupervised or unlabeled data, but the labeled data is pretty sparse. And that's definitely an interest of mine, because just data is so expensive. In some instances, data is so expensive to get. And, one of the things I do, we have like We have about 1 billion unlabeled points, but it costs us $10 or $15 a labeled point to get a labeled point. So if we can leverage these unlabeled data to make better decisions, it's really effective. Okay. So where's machine learning being used today? These are some places. Face detection. These are, handwriting detection. Email's been used for a long time. The voice recognition on your phone. Question answering, like IBM's Watson or the Google search engine. Forecasting weather on these wind turbines. Stock trading, recommendations, spam detection, and law, like that example I talked about earlier with the extracting topics from documents. Okay, where else? Spacecraft. This is the Hayabusa spacecraft. In 2003, it landed on an asteroid by itself. It was so far away, the feedback from the controls at Earth to the asteroid were too long, the delay was too long, so it actually employed some artificial intelligence to land by itself. Self-driving cars, there's tasks to identify whales, predicting strokes, lots of fighting financial fraud, there's lots of places. Oh, there's a website called Kaggle. Has anyone here heard of Kaggle? No? They hold data mining competitions, and you can go there and register and take part in the competition. And so this identifying whales was one of their competitions. It's if you're interested in data mining, I would go there and see what they have. It's Kaggle. Okay. So why is this stuff useful? Well, one of the greatest things is you don't have to be a domain expert to make a prediction or forecast. And there's two examples of this that are spelled out in detail in this book called Super Crunchers, where some guy with a machine learning algorithm beats an expert. So one of them is a law professor. I think this is a law professor at Yale, took on a machine learning model and lost at predicting what the Supreme Court would rule, how the Supreme Court would rule. And a second example was another economist, I think he used regression, out-predicted wine snobs at what wine would taste the best. And so he used things like weather, soil, those sort of variables, and beat the wine snobs. So it was interesting when I used this slide to the high school students. I said, oh, look, these wine snobs had been drinking wine for 20 years, and this law professor probably had an LLM, which is like 2 years after his law degree, which was 3 years, which after his undergrad, so he had probably had 9 years of school outside of college. And I said, look, some guy with this model beat him. And so they were like, great, we don't have to spend a lot of time in school. And then the teacher who was there, he got a little bit upset and was like, wait a second, guys, we still want to stay in school. This doesn't mean that you can quit right now. And I'm not trying to say that, but I'm not trying to say that I'm better than these experts who have 10 years of study in a field if a model beats them at predicting something. But what happens is we're often asked to make predictions on things that no one has studied before, or no one cares to be a domain expert. Like if you think of the Amazon recommendations, they're asking the algorithm to recommend you things based on your past purchases, and your past purchases may be baby toys and World War II videos, and there's just no one that's an expert on you and your particular interests. Or you may be working for a website that sells, I don't know, something, cat wigs. I actually have seen this for sale. So there's just not a field of study of cat wigs, but you may want to make some recommendations based on this, or you may want to predict which customers are going to leave or which customers are going to be good customers, things like that. That's really why this is useful, and I think it's become even more popular in the last 10 years or 15 years. Okay, now I'm going to go into a few coding examples that were written in Python. And I'll just show you. Okay. This was just a simple classification using something called support vector machine. And what you do, how many people here are familiar with Python? Okay, so I don't have to talk about everything. It's from this, there's this, all these examples, I've got 4 code examples. They're all from the same package called scikit-learn. And so you can go to scikit-learn.org and look into plenty of this stuff if you want to see this. So, okay, pretty much the X, capital X is our matrix of features, and Y is a vector of labels. So we just create a classifier, this support vector machine. This SVC stands for support vector classifier. It's the type of classifier that's really powerful, it's really useful outside of the box. And we just here we would train it on line number 9. We train it on our data, so we fit our model to this data, our features, and our labels. And then in the comments here, I printed out what would happen if you printed out this classifier. So it's a class, and it's got some attributes you can set. And then we can make a prediction on it. So after we've trained this classifier, we can make a prediction. And I put in this input feature vector here with just two features, and it would output a 1. So we're asking it to give us a 1 or a 0. So that was pretty straightforward. So problem with this is if you were to look at all these, features, or someone was ask you what they meant, and you were to dig into these attributes, you would say, I really don't know. I have a hard time understanding what these mean. So there's another type of classifier which I would suggest you use called decision tree, and we would train it in a similar way. So the code looks pretty much the same. We just have a different type of classifier, and this time the decision tree, you could take this and you can explore the tree itself, and the tree will tell you like why it made decisions, and it looks like basically it would look like a flow chart, and you could take this and understand the data better than you could with the support vector machine on the previous slide. Okay, yeah, let me just repeat the question. So the question was, can you explain what the data sets are supposed to mean? And you asked if you were right, but I'll explain it, but you're right. So this is a matrix, or it's got two, actually it's a list of lists. So the first list has these 2 features, 0 and 0. And then the second one is 1 and 1. And then these are our labels, and the first one label is 0. So this is saying that if we have the input feature 0, 0, then we've observed that the output will be a 0. And then similarly, if the inputs are 1 and 1, the output will be 1. And then this is a oversimplified toy example, but you'd have many thousands of these, and they wouldn't be clear cut. So there might be some that I might have 0, 0 one time where the label is 0, and I might have it again where the label is 1, and we're just going to. So we couldn't make we couldn't say to make a deterministic classifier that's going to completely classify everything. So sometimes there's some slop and there's some errors, and that's expected because we have noisy data and stuff. Does that answer your question, or to explain it properly? Okay. Okay. What I want to say was, in real life, data doesn't always come this easy. So I spend, and many other data scientists spend between 50 and 90% of our time getting the data into this format, getting it into these 1s and 0s or in these simple features. And the reason why this is there's a number of reasons why this happens, but sometimes we have the wrong format, sometimes things aren't being recorded, sometimes other people in the organization don't want you to have the data. They might feel they're doing a poor job, and they don't want you to start analyzing what they're doing. So I'd spend at least 50% of my time on activities where I'm trying to get the data. And it might mean talking to people in the engineering organization, trying to understand what they're doing, or talking to people in other functions. How can we get this data so we can make predictions? And that's a real problem. And there's a number of tools out there that try to help you to solve this. And there might be a demo. And today, I think these are they're useful tools. Sometimes, as an engineer, you're like, I don't need help importing data. I can parse out data, whatever. I know how to write code, but it might just be easier sometimes if you had a tool that can do some of this stuff for you, at least. If it's in the wrong format, change the format properly. Or maybe you could just spend some time investing in writing a set of tools that will convert things. That's one of the problems that we commonly face. Okay. I'm going to go over 2 more examples. This is called regression, and it's just predicting the numbers, and it's similar to the classification examples, and I'll show you. So I have 3 inputs, and then 3 features vectors here, and then these are my 3 numeric values. So in the previous example, I was trying to predict 0 or a 1, so a discrete class. Here I'm trying to predict a numeric value. So the code looks similar. In this example, this regular linear regression is similar to what you can do at Excel and what I did at the very beginning of the presentation. And what comes out are these coefficients. And so after we've ingested this data and we've learned from it, we can take this to management or something and say, look, if you have what the data is telling us is if you have whatever, I don't know, we can assume, okay, these examples we can use the example of the baby's weight. So we can say like, all right, this is saying that if we take 0.5 times the baby's weight plus 0.5, then we'll get the baby's height. That's not true. That's true, but the actual numbers from the data were like 12 and 0.5 or 0.9 or something. Anyways, this is what we've learned, and this is what's important. And it's important to understand what that means. Sometimes data is difficult to get. And this often is the case in the medical field, where you might be predicting if someone lives or dies. And you might have a rare disease that only 27 people in the whole country have gotten. And you may have wanted to make the best prediction possible for these people. You're trying to predict if they're going to live or die, or if they have something. It's serious business if you think about it. So you've collected a whole bunch of features. But what happens is if the number of features is greater than the number of examples you have, you run into some problems mathematically. So in the problem you'll run into is you'll overfit. So you've got here in this example, I've got 4 different, my input features have 4 different features, but I've only have 3 of them. So I'm trying to figure out 4 different coefficients, but I've only got 3 pieces of data. And you can fit a perfect line to that. And the reason that's a problem, because it's going to give you the wrong answer. It's going to totally fit this. So there's something called ridge regression, or there's another one called the lasso, where you can actually control this, and you can tune it, you can dial it back so it's not going to what we call overfit the data. And this is an example using ridge regression. So similar to the linear regression I used in the previous example, I just fit the data to this, and then I think I'm actually missing a line. Okay, and then you print it out. I print out what I have, and finally we get these coefficients. So this is something to keep in mind. Like if you have the number of features you have is greater than the number of examples you have to use something other than just straight up linear regression. Okay. Next, I'm going to talk about semi-supervised learning. And I just have, I don't have any code for this. I didn't bring any code. I just have this cartoon. So semi-supervised learning, it says, can we use labeled and unlabeled data to make decisions? So on the left-hand side, we have what we were just doing, this supervised learning, where we have these. We predicted the class of these is a 0, and the triangle is the class is a 1. And then we fit some line that said their decision boundary is this red line, and it says everything on the left side of this red line is a 0, and on the right side is a 1. Okay, that's great. But the data is expensive. Like I said, in my case, it was like $20 a data point, and it could be someone living or dying also, and that's expensive data. So if we have this unlabeled data, and in our medical example, maybe this person they have the disease, and the disease hasn't run its course. So these are the green dots, and we don't have a firm answer if they're going to live or die, or we just don't know the label because it's expensive to get. But could we use that? Is there a way that we could use that data to make better decisions? And that's what this task of semi-supervised learning does, is we can take these green dots, these green data points, and we can essentially, in this example, it's like, you can think of this as clustering, or we can take a step first and go through and assume and assign some label to these green dots. So based on their proximity, or based on something else, their proximity to labeled data, we can say, okay, we're going to assume that all these green dots, they'll take the label of whatever they're closest to. So these are all going to be 0s, and these guys are closest to a triangle, so that means they're a 1. And then we can go through again and train a model second time, and this time we have a new decision boundary, which is this new red line. So even though we have the same labeled data, we have a different boundary. Our boundaries actually changed, and we have a better line. So that's something that is applicable to something I work on, and it's very important because sometimes data is expensive to get. Okay. Next, I want to talk about like how we go through and we build these machine learning models and how you do it. So let's say you wanted to build some model to predict. We're going to predict the kid's height, and we're going to throw it. Okay, we'll do two things with it. We're going to, one is try to understand it and try to communicate it with the rest of our organization. And the second thing was we're going to build an application. So let's say we're trying to predict the height, but these kids are too squirmy and they won't sit still long enough to measure their height. So we're just going to weigh them, and then we can predict their height. So what I've done earlier is just we get some data and assume it's not a problem to get the data. We put it into some machine learning package we got, and we get this model out. That looks great. That's cool, right? Okay, but there's a better approach. Like, what's better is we actually can split up the data into a training set and a test set. And we're going to test how good our model is, because if we just did this, like in this example, who knows? There's no feedback. We're not measuring the performance of it. So we split this up. We split up our data into the training and test set, and we measure something. We get some number like our error. So in this example, it'd be like mean error. And then what we can do is we can go through and iterate. So we can go back and we can change some parameters in our machine learning code here. We could maybe get more data. We could check the code to make sure it's doing the right thing. There's a number of things you can do, and you can iterate on this. And this is a common task, because sometimes what's going to happen is you're just going to your first approach isn't always going to be correct, and so you want to iterate through this multiple times. Okay, so this brings up the question of how to do this in a modern development environment. Or what happened to me was our company is growing quite quickly, and when I joined, I was like engineer number 3, and we've grown to maybe 20 engineers, and we have a manager who asks us to do agile development, and I'm like, okay, that's fine. And so a lot of us know how to do agile. Maybe, okay, who here knows agile development and how to do it? Okay, everyone or a lot of people. We know how to do it with features and creating things. So if you're making a website or an interactive website, you might say, oh, add this feature, and then the engineer goes and does it, and they're done, and that's it. But with machine learning, or when we're doing, with machine learning, it's not that easy, because just implementing it the first time doesn't mean you're done. Just even if you meet the requirements, defining the requirements is a problem. So there was one guy I was working with, and he had worked at some pretty famous companies, and I asked him to implement this thing that would match people's names with other people's names. So sometimes there's a mismatch, and he said, great. And he researched this, and in one night implemented it, and it was jaw-dropping how quickly he had implemented this. And he said, okay, I'm done. And then I said, well, what's the accuracy? And we looked, and the accuracy was like 3%. And I was like, you're not done. You're nowhere close to done. But I see a problem in the modern work environment where if someone's they spend their time taking user stories and implementing features, and then finishing those features. they have a hard time transitioning to this world of maybe machine learning where we have to iterate multiple times on things. So what we've come up with is a way to implement this or adapt this to agile development where, okay, so our sprints are a set of experiments. And at the end of each sprint, we will test the target accuracy. So we set up a target accuracy, let's say 90% accuracy. So we don't know how many sprints it's going to take us to get there. And actually, we don't know if we can ever get there. But what we do is we set up a series of experiments, and each experiment takes one sprint. And at the end of that sprint, we actually allow like 2 days before the sprint review for what's called headroom analysis. And so we'll say, okay, here's the errors you got, and here's how much we need to go. We need, maybe you have 80% accuracy, but our target's 90%. What were the errors you got? And we'll look through the errors, and with some so-called experts to say, and it's to analyze those errors and say, okay, these errors were caused because we don't have enough data, or the algorithm isn't that great. And what that does is it gives us a guess at what we can do in the next sprint to try to close that gap. And this is I think it's a pretty powerful method to approach this or to try to meet your goals. And a lot of this I stole from IBM's Watson. So they did something, they published a paper on how they used agile development in developing Watson. Do you guys know what Watson, you remember Watson, you've heard of it? No? Okay, yeah, everyone does. Yeah, they use a lot of this, so I borrowed a lot of it from them. But it keeps the Scrum Master happy, and we can quickly reach our goals or decide we just can't go any further and we have to stop there. Okay. I just want to talk about quickly this interpretable machine learning. So some of these examples I showed were difficult to interpret. They might be mathematically complex, or you just don't know what's going on inside. And sometimes you have to explain to the Bobs what you do. Does everyone know what this is? Okay. Does anyone not know what this is? Who these guys are? Okay. So people say, what is it you do? And you have to say, I predict stuff, or I build software that predicts stuff. And okay, it's good that you can explain it. And the other thing is that you can take the stuff you've learned and you can give it to people in the organization and they can spread it out. You want everyone to be on the same page and thinking alike and thinking like you. So it's better that you have stuff that is interpretable. And I'm saying like black box models, a lot of these some of these high performing things, like if you look at image prediction, you look at like deep learning, it's just the results are a mess. Or if you look at in a lot of classifications, like support vector machines with a kernel, the results, you have no idea what the results mean. So things like a decision tree is easy to interpret. So sometimes you may want to build even two models, say like a single model that is high performing that you'll use in production, and another model that you're going to explain to the Bobs and explain to other people. And there's a series of algorithms called like decision lists and sparse integer lists. If you're interested in this, like that they generate a series of human readable models based on the data. And sparse integer list is like that regression, but it constrains the coefficients. So the coefficients can only use one of three numbers, like a 0, a 1, or a 5, and powers of 10. But so you can quickly, so everything is is either not in the model or it's a 1 or a 5. And you can generate some pretty good things with that. So I would, if you're interested in that, I would check out its decision list and sparse integer list by someone called Cynthia Rudin. Okay. Next, I want to talk about this buzzword, this thing called data scientist. So here's my quiz for you guys. What is a data scientist? Is it A, a cross between a statistician and a developer? Is it B, a developer who knows some machine learning stuff? Is it C, a buzzword to attract developers? Or D, all of the above? Who? D? Okay, yeah, I agree. Yeah, so we hire developers and we hire what we call data scientists, and what we found is a lot of people are applying for the data scientist position are good developers, and they just think that the word data scientist is cool and it's fashionable, so they're applying for it. And we've said, well, we actually don't think you're suited for the data scientist position, but how about the developer role? And they said, yeah. And so we found out, I'm kind of spilling the beans here, and if everyone used that technique, then our competitive advantage is going to be gone. But that's something we've learned over the past year or so, is that we can hire good engineers by setting up an application for a data scientist. And the other thing is, data scientist is kind of a vague term. Is it someone who knows how to build models? And I've seen people say, I'm a data scientist, but I won't code, and I wouldn't hire anyone like that. But generally we don't demand the same level of I don't know, engineering maturity from a data scientist that we would from an engineer. Like, you guys are probably all Java gurus, and our data scientists probably aren't up to that level, but we hire them for other things, and maybe we can train them in some of these other techniques. So that's like the last of the things I've learned from the trenches that I wanted to share with you guys. Okay, so that is all I prepared to present. I had some backup slides, but this is all the prepared material. Are there any questions? Anything I can answer? Oh, hold on a second. Can I just answer the first one? It's early. I'm going to forget it if I don't answer the first one. So the question was, I said I spend 50 to 90% of the time scrubbing the data, and that's true. Are there she asked, are there any recommendations I have for that? Or do we just make things ourselves? And so the answer is yes. Okay, so in the past, we've just been making things ourselves at my current employer, just because we were a scrappy startup. But now that we have a little bit of funding, we definitely are looking at some tools, and there are a lot of tools. The thing is, it depends what role. So like for a developer, I think it's better to just write everything yourself, because you know what it does, and you know what format you want it in. I would try to reuse that as much as possible. I can't tell you, I've probably rewritten the same thing like 10 times. So I think it's worth spending some time to develop develop your own code that can do that, but this is reusable as possible. Now, there are tools that I've used, and we've looked at a couple of different vendors they weren't for me, but they were more for salespeople or engineers in the sales organization, so they could pull in the data in a different way, or they could pull it in any sort of way. And there was something called SciSense. We're looking at, and I believe actually we used SciSense, it's S-I sense, and then the second thing was, I forgot the name of the second one, but there are a couple of these. SciSense has been good for us so far. Okay, now what was your second question?
Similar for machine learning algorithms, if you have something where you could, get those algorithms out of the box and switch between one out of the other and experiment and see, which one fits your needs best.
Yeah. Okay, so the question was, are there any out-of-the-box algorithms for machine learning that you can use and experiment with out of the box? Okay, there is a toolkit called Weka. It's from New Zealand. These professors in New Zealand wrote it, and they actually have a GUI, and you can sit there and you can play with the different algorithms. And it's Java-based, so you can later take out the jars and you could use the code outside of the GUI on your own. So Weka's one example. The problem is it chokes on larger data sets. So they have something called MOA from the same authors. And if you guys are familiar with birds, does anyone know what MOA is? It's an extinct, like ostrich type, huge, yes. It's a humongous bird, but it's extinct. I think it was from like the Stone Age. And they got another version of that that's supposed to be better for larger data sets. I haven't used Weka too much. I find the thing is, when I was preparing these slides, I wanted to do it in Java. And of course, there's the problem with Java being verbose, but the other problem was I just couldn't find a single thing, a single repository, a single project that had all the different algorithms. Like I use, don't get me wrong, the Java algorithms are awesome and they outperform the Python ones, and that's what we use in production, but I don't have one particular source for each of the tasks I want to do. So for support vector machines, the classification, I use libsvm, it's from Taiwan, and then I use, for like those frequent item sets, like the diapers, men implies beer, I use something from England, and just like, it's just a bunch of different things. So I think the closest you can get is Weka. W-E-K-A. What's that? Oh, MOA, M-O-A, I think. The Python was, okay. Let me see. I've got, let me just search. Yeah, so this is Weka. See the bird? Okay. And then, oh, there's a book. The book's pretty good. It's in its 3rd edition. And it's kind of an introduction to data mining and machine learning. I like that. Massive online analysis. Yeah, so here's the MOA version. And then, oh, the Python stuff I was using, okay, is called scikit. Scikit-learn. And they have this flow chart. It's interesting. Where is that? Yeah, they have this flow chart, this chart that says what you should do. I'm not sure I 100% agree with this, but I thought it was pretty interesting. Like, you've got this much data, and it's labeled. It's labeled. Then you should do. It's labeled. Then you should do classification. And okay, start back here. You've got some data. You've got less than 50 examples. Sorry, you need to go get more data. But you've got more than that. Okay, are you predicting a category? Yes. Okay, so it's labeled. Then go to classification. It's not labeled. Go to clustering. I thought, yeah, you might like that also. That's from the same site. Question? Yeah. No, we do. I mean, we have 1.5 billion documents we have to process daily. So we have a pretty expensive bill. I personally prefer C++ to Java over Java. Yes, and I think, but what's the speed up? Maybe you get a speed up of 2 there. And in my previous company, I'd written things in C++. It was like Python to prototype over a small data set or a medium data set, and then C++ to do the large processing. But like at the current employer, it's a Java shop. And the argument, okay, so I can argue we get a 2x speed up over going from Java to C++ is probably not worth it. Like, we could just throw more machines at it.
So you have a more distributed model, like, are you using like a base system where you just...
Yeah, yes, we... Yes. Yes, we definitely use like native Hadoop. Things are written on top of that, so we don't use anything like Pig or Cassandra or the Spring XD. I saw those are cool. It's just, I have to worry about the algorithm and I've definitely looked at that, and I've written Hadoop jobs myself before, but currently it's just not, there's other people whose job that is. So my job is to get it, like, the algorithm working so it could definitely be done in a high throughput environment, but I don't have to write the code myself. So I leave that up to someone else makes that decision, not me.
But do you put it all on like one machine and just like, do it all there, or do you basically farm it out to multiple machines?
Oh yeah, definitely farm it out to all the machines. So like the things that I'm doing we're looking at text, maybe 10K of text in the English language, and we're trying to figure out what it means, basically turn that into a relational database with just a few relations. So it's not that I don't have to join a lot of data sets. So this can be distributed very easily. Just take the same code, copy it onto multiple machines. So Hadoop's really good for that. It's just, yeah. Oh, okay, the question was, since we're a Java shop, do we use any combination of Solr and Mahout? And the answer is, I like Solr, but someone else made the decision to use Elasticsearch. Okay. Yeah, it's some form of Lucene. Definitely. There's some really awesome things. Yeah, we don't use Mahout. I can tell you why. You can even look, the creators of Mahout have moved on to something, or some of the creators of Mahout have moved on to other versions. And what the problem with Mahout, especially with recommendations, is it's all batch processing. So every night you have to run through your whole data set and make a recommendation for everybody to every item. Like I have to recommend something to this guy, which he probably wouldn't buy, and something to you, which you probably wouldn't buy, but we have to make that calculation. So what these guys have figured out, and which is really awesome, is that you can use Lucene and Solr on top of Solr, make recommendations in real time. You can update the data set in real time. So like if I was making this for Amazon, you made a purchase right now, I could update the index, and then within a couple seconds, as soon as the index is updated, I can make a new recommendation for you. So the guys who've written Mahout have learned that building things on top of the Lucene indices is better than batch processing. And I think, yeah, it's awesome if you do that. Under the hood, what happens is when you're doing these recommendations is you've calculated like maybe a feature vector of all the things you've bought, and then you want to compare it to everyone else in the database. And mathematically, that's a lot like it's a cosine similarity, where you're just looking at the similar items, and if it's binary, it's just adding up how many similar items you've bought together. And that's basically what a search index does under the hood. So it's pretty easy to do with something like Lucene. Oh, you're not comparing like if something's been bought or not? Something.
So like maybe just throwing numbers out there. 3 is close to 5, so it might be similar. Like how you can pull that.
Yeah, you can still do that. The thing is, you just have to rewrite it's called the analyzer class in Lucene, so you can rewrite that for different things. So that's what I would do. Okay, were there other questions?
A lot of statisticians use programming language like R and SAS.
Yes. You can use R and SAS in place of this. So like SAS, correct me if I'm wrong. Okay, I'm sorry. To repeat the question was a lot of statisticians use things like SAS and R, and where do they fit in? And my answer is, first, SAS, I think you have to pay for licenses. Is that right? Yeah, and I know some statisticians that use that. And then the second one was R, and R, a lot of people, they'll use either R or Python and these like Python libraries. And I think it's just a matter of preference. So my background, the first programming class I had in college actually was in MATLAB. And so like these numbers, when I'm doing matrices and things, the NumPy, the numeric library for matrix multiplication is really like MATLAB. So that's why I chose Python. I think Python's superior to R, but it's there's a religious battle there.
I noticed a conspicuous absence in your talk of artificial neural networks. Can you maybe place that within this context?
Yes, I am so glad you asked that question. I have been prepared. Oh, sorry. The question was, I noticed absence of artificial neural networks in your talk. And what was the second part? Could you talk about that, or was it?
How do you see it fitting in this context of data mining and pattern matching and prediction?
Yes, I'm really, okay. And second part was, with these artificial neural networks, how do you see that fitting into the context of this data mining and machine learning? And I'm really glad you asked that question. I've been prepared, the past 2 talks, I've prepared for someone to ask that question. And this was the first time it happened. So, okay. I think with the artificial neural network, it's useful for some things like image prediction. And so the short answer is the short answer is neural networks are useful for some things like image prediction or image classification. And they are not as powerful, they're not as effective as other methods like the support vector machine or random forest for other things, especially maybe for text. Now, with the advent of GPUs, we're seeing there's a lot of research done now in what's called deep learning, which is like multiple layers of neural networks. And it's very computationally intensive, but you can get 100x speed up by using a GPU over your CPU. And that's kind of the frontier right now of machine learning. But there's not a lot of theory there. It's just a lot of practical things. Okay. The real reason, or the reason why these neural networks came out is people studying AI had tried to imitate the brain. And they thought that, okay, the brain's made of these cells, these neurons, and they made a function that has a response function similar to a neuron. And then they thought they could create an artificial brain. And that was an experiment. But I think it's a lot like in the early stages of flight when people tried to make bird wings, they strapped bird wings to themselves and tried to fly. And they wound up with broken bones. And the guys who did, first master powered flight used something that really didn't look like a bird. Like if you look at the bird's feathers, it's got almost an infinite number of surfaces, where the Wright brothers' first plane just had 2. And it was very difficult for them just to figure out how to control that. So I think the early experiments, people said, oh, this is, with AI, they said, okay, we got these neurons and we're going to throw these out. We're going to try this experiment and see if we can create an artificial brain. And it proved useful in some contexts. And this is also like where I believe the study of artificial intelligence has been bastardized. So the true artificial intelligence, like the guy who coined the phrase, was studying medicine, and he was trying to understand how the human brain works, and he found out the best way would try to be to recreate one. And what happens is, in that effort, we find things that are mildly successful, and we run off on the tangent of those. So the single neural network didn't recreate the brain. That's fine. But it was useful in things like image classification. And I think it's just useful to, and that's fine, we can use it. And machine learning is just a bunch of useful hacks. It's not trying to recreate human intelligence. But I think it's important to keep that in mind. To keep in mind like that all these things in machine learning, data mining, are just hacks that can provide useful answers. Like if you look at Watson, it just answers questions. It can compete against what's geniuses at Jeopardy, which is a task that intelligent people are supposed to be able to play. But if you look at what it does, it's just really fancy search. It's really fancy text search. So no one's going to say that Watson is like a sentient machine or an intelligent machine. I think that's what I'm trying to get at, is you just need to keep in mind that a lot of these applications are just useful tools, but they're not super intelligent machines.
So to what degree do you see the use of neural nets in the data mining context?
Okay, the question is, what degree do I see the use of neural nets in a data mining context? Yeah, like I said, it's useful in certain things, like it's definitely image classification. It's the best. It's the state of the art. People are trying to do it with natural language processing. And this is recent. This is recent, like deep learning sort of thing, which is like multiple layers, 3+ layers of neural nets. I hope that there's some advances there. I think we'll see some useful applications, but I think it's going to be limited to just there's going to be better algorithms for certain tasks.
So image processing aside, it's a niche or small player and potentially may grow, but the jury's out.
Yes, yes. Okay. Any other questions?
I came across that prediction IO on GitHub the other day. Have you used it? Any opinion on it?
Oh, the question was prediction IO on GitHub. No, I haven't used it. I've heard of it, but I haven't used it. Google's got a prediction API also. Oh, I have some friends who are farmers, and they asked me about machine learning, and I said just look at Google's prediction IO. Like that would be the first step I would point to, things like that. Okay, so the question was, let me paraphrase. How do you approach a problem? Let me paraphrase this. How do you approach a problem where you can prototype it on a single machine, but you're going to encounter the problems or complexities you would get on multiple machines, like for a real world? Is that a fair paraphrase? Yeah, okay, so the rest of the question was, she was worried about the loss of information at the edge of the data set if we restrict it to a single machine. And so I'd say the answer to the question is you really can't duplicate on a small machine exactly what you're going to get on a full data set. So there's things we want to look for that are outliers, and they're just not going to, you won't have those, if you look at those on a small data set, you won't know that they're not that frequently occurring. You wouldn't know that until you ran the whole data set, and then you could say, wow, these things actually were not that frequently occurring. So you won't know that. So there are certain things you just can't do or you won't know the answer to when you're just doing on one machine. You have to actually do it on, you have to run the whole cluster, or you have to run your whole job. And it may take 24 hours, and it may take 96 machines or something. And that's just, I think that's one of the, it's a problem, but I'm not sure how to approach it. So the other part is you try to duplicate or you try to get a good example on a small machine before you mess around with that stuff. So, like for a graph, you can simplify a graph and test things out. But yeah, I don't think you could totally foresee all the problems until you run the whole data set. Okay, I'm sorry, what kind of model?
I used ML in the past, so that's something as an example, but whatever it is.
Okay, so the question was, what are the challenges to, I'm sorry, could you repeat the question?
Just model refinement.
Okay.
Of big data. So we talked earlier about batch workloads and the challenges to having velocity in results.
Yes.
So like a recommendation, you could see the same kind of problem in any model that you need to train over time, right? When you're applying it to something like Hadoop, and especially with unsupervised learning, how do you get better refinement in your model to make more accurate predictions over time, and how do you do that with velocity?
Yeah, okay, so the question was, how do you get better refinements to your model, to a model, any model, let's say, and how do you do that with velocity? And velocity is like the pivotal tracker definition of velocity, like, how do we make rapid adjustments? How do we make rapid improvements? Is that a fair paraphrasing? Okay. So, I mean, one is, okay, you'll try to do as much as you can on a single machine, on your laptop, on a representative. Try to get the data set as representative as possible. I think that's going to be the quickest one because, like, if we're using things on EC2 and we're actually limited to the number of machines. So even if I want to use more machines, they're just not available, or we have to make a special phone call to get them available. So that is a huge bottleneck. Like, if you have code that works and everything that works, it's still, and you want to run it across the whole data set, you're just limited to either the size of your cluster, pretty much the size of your cluster. So that's something. Another example would be, can you test the intermediate results? Could you, so a lot of these MapReduce jobs are like a derivation from like the single core version. So there's going to be at least one intermediate step, maybe more. You might have training a single algorithm may take 10 MapReduce jobs. Like if you look at clustering or some support vector machine, the MapReduce manifestation, it's multiple MapReduce jobs. Like clustering, you do a MapReduce job for each iteration. So you might have 50 MapReduce jobs. So you want to break that down and say, can I look at it after the first or just after the map step? And can I look at the results there and make some sense of those? And I think, yeah, writing as much as you can, in Java or C++ on your machine, on one machine, and then processing as much as you can, maybe within 1 hour or so, will give you a huge head start over trying to run it against the full data set and tripping when something goes wrong there. Yeah, in my book in 2012, they were like, oh, you got to talk about MapReduce and you got to talk about big data. And I think if you look at the Korean title, they even have MapReduce in the, they have big data, the word big data, and it's such a buzzword. Yeah, right here it talks about big data. It's such a buzzword, and I think you can just get away with so much by writing your stuff in lower level, you know, in Java or C++. You can get away with so much. Like I see people, they'll write it in Python or Ruby, and then they'll try to run that against the whole data set, and it will explode or just take forever. Like in Python, everything's an object, and it takes so long to package things up, and you can just do so much by writing it in a lower level and testing it on a single machine before you have to go to MapReduce. Yeah, the other thing is a lot of those algorithms, the speed up is actually slower. So if you look at the recommendations is a great example. The recommendation, if you did on a billion recommendations on your laptop, or you did it that's the single core version. If you did 1 billion recommendations on MapReduce, the MapReduce version is takes 8 times as long. And I'm not talking about like the 2-minute overhead it takes to spin up a machine or load stuff into HDFS. Just it has to be rewritten. It's rewritten in an inefficient way, so you can get a lot done by using one machine. Yeah, go ahead. Yes. Okay, so the question was, sounds like you spend a lot of time finding the representative data set, doing ETL, and then feature inclusion or exclusion. So yes, that's true. I'll get to the ETL part in a second, but the first part is, I didn't talk about that in this presentation, was like feature engineering, where not only getting the features, but let's say we got 20 features, we can improve that by throwing stuff out. And there are algorithms like forward search or backward search, where you start with all your features and you add on a feature. You'd start with one feature, forward search, and you'd add on another feature, and then run your algorithm and see if you get better results. And with that, you can throw out data. And to the point, you can there's algorithms like there's one called liblinear that are specifically designed for large data sets, and they're really fast. And but the accuracy is not as good as so for like support vector machines, liblinear is not as good as libsvm, but it's close. And it's a lot faster. So another thing is you can use suboptimal algorithms. You can use them to speed up your velocity or your development time. And with things like feature selection, that will help. I haven't seen like doing feature selection in something fast like liblinear and then moving to something a little bit slower. I haven't seen that be a problem. Like it's okay to do the feature selection on a faster algorithm and then change that. Okay. Any other questions? Okay, well, thanks for coming out.